Okay, in this video, I'm going to show how to use SageMath to work with the symmetric group. So here's a specific example. I've done it by hand in a previous lecture. So let U and O be elements of S6, the permutation group on 6 letters, given by U is equal to this permutation and O is equal to this permutation. As a reminder, what does this mean? Well, remember, permutations are functions. In this case, functions from the set consisting of numbers 1, 2, 3, 4, all the way up to 6 to the same set. And this function u sends or takes 1 as input and gives 5 as the output. It takes 2 as input and gives the number below it, in this case 2, as output. Similarly, O is a function on the same set of numbers 1 through 6 that takes, for example, 6 as input and gives 2 as output. Note that in each of the second rows, none of the numbers are repeated, and every number occurs exactly once, which indicates the property that u is a bijective function on the set of numbers 1 through 6. Okay, so then we want to compute u times o squared, where the group operation under S6, or the symmetric group on 6 letters, is function composition. Okay, and then we showed in a previous lecture how to actually do this by hand. It was quite tedious, but it's simple if you use the cycle notation. Okay, so here's how to do this in Sage. So first we need to create the symmetric group on 6 letters. That's a fairly simple command. G is equal to symmetric group, and then type in 6 there. And then I ask, what is G? Well, Sage says, okay, it's a symmetric group of order 6 factorial. That's 720 as a permutation group. Okay, and then now I want to tell or create an element U in this group G that belongs to, or that comes from this definition here of U. And so one way to do that is, well, take this second row, that's 5, 2, 4, 3, 1, 6, and enter that like so. So this is coercing or telling it's in G, this list 5, 2, 4, 3, 1, 6. Okay, and then if I ask Sage, what is U equal to? It actually gives me the cycle notation associated to U. It doesn't give me the, I don't know what kind of notation this is called, but the tuple notation or what have you. Okay, and again, why is this correct? Well, let's see what U does. U does indeed send 1 to 5. So that's consistent with the cycle notation here. Does U send 5 to 1? Well, looking at it over here, yes, U does send 5 to 1. And so, okay, we can believe this here. Now, if you want to get back the other initial notation we entered, the domain function will work. U.domain will give you back this, this notation here. Also, the U.tuple notation will also give this, but I omitted mentioning that because the tuple and the cycle notation can be potentially confusing. Okay, now let's do the same thing with O. O is this element given by this function here, and so let's just take the second row, 3, 1, 4, 5, 6, 2, throw that into G, and define this function O. And then when we ask what O is, well, it gives the cycle notation, gives us something different. This cycle happens to be a cycle of length 6. Okay, and then now we can finally ask Sage to figure out our question. Again, the question was compute U O squared. Now, what you need to do, unfortunately, is switch the order. And again, this up here was U times O times O. You need to ask Sage to do the opposite. O times U. That's what I asked it to do. O times U is the same as O squared times U, and then it gives me back this. And now why do we have to do this? And that's because Sage works from the left to right. Again, it's a convention, and various sources use different conventions. Most people or books that I've encountered work from right to left, which is the opposite of what Sage does, but there's good reasons for why either choice is used. The reason the book and I work from right to left instead of what Sage does left to right is because we're really thinking of these elements U and sigma, or sorry, U and O as functions. And when you think of this as functions, you work from the right to left. You input, if you want to say what the input of one is or what the output when you input one is, you start putting one right next to this O squared, and then, as I did in a previous lecture, compute what O does to one, what O does again to the O of one, and what U does to that result. Anyway, so once we, here we are. So Sage gives this result, and this is the cycle notation. We want to compare our answer with what we did in a previous lecture, where we got 3, 4, 1, 6, 2, 5. So we need that domain notation, if you will. So I did the same thing, sigma squared, sorry, O squared times mu, and then I put parentheses around that, and then applied the domain method, and then it gave me 3, 4, 1, 6, 2, 5, and I believe that's what we had computed earlier. Okay, yeah, exactly. So that's the answer to that question. Then I wanted to just mention some other commands of working with the permutation group, or the symmetric group, I should say. Okay, so then we can ask for the order of any element. So the order of this element U is 2, and the order of the element O is 6. How can we figure that out from the cycle notation? It's the GCD, sorry, it's the least common multiple of the lengths of the cycles. So U has cycles of length 2 and 2. Their least common multiple is 2, and so that's going to be the order. I'll explain that in another lecture if I haven't already done so by the time you're watching this video. Okay, and then O is a cycle of length 6. The LCM of that is just 6. Okay, so then that's the order function. Then you can also compute the inverse of an element. Then you can compute the orbit of a specific number under a particular element of the group. So for example, if I take U, that again is this element or function that switches the 1 and 5, switches the 3 and the 4, and ask what is the orbit of 4? Well, the 4 gets sent to a 3, and the 3 gets sent to a 4. And so the orbit of 4 is basically the cycle containing 4, 3, 4. Okay, now let's just add for fun another element, and I'm going to call it W. And here I want to enter it with cycle notation. I just did this to show you how to enter an element in the group with cycle notation. You have to put it in quotes like so, and then here are the cycles, and then I ask Sage what W was, and it gives me back this. Okay, fine. I'm missing a 5 here. I kind of did that on purpose. The cycle notation, we don't typically list elements that are part of cycles of length 1. In other words, W does not do anything to 5. If you give 5 as input to the function W, it gives back 5 as output. Okay, and then in the in the domain notation for W, we get this. Notice that 5 is indeed in the 5th spot. So that's good. And then the cycle type, here's a new command. The cycle type is 3, 2, 1. That tells you the lengths of the cycles of, in this case, W. W has a cycle of length 3, a cycle of length 2, and then that 5, which we typically don't write because it's a cycle of length 1. Okay, then let's create a subgroup of this permutation group consisting of O and U. I just chose 2 of the elements, and I want to create a subgroup. Okay, so here's the command for that. H is equal to the permutation group generated by O and U. You put O and U in the list. In other words, in a closed or square brackets. Okay, so then we have this permutation group H, and these are the 2 generators. And if I asked for its size, I get that H dot order is 720. And I was like, oh, that means that H is the entire group. So, and then I asked Sage, is G the equal to H? In other words, are they equal? And the answer is true, because first of all, obviously they have to be true because G has 720 elements, and H is a subgroup that happens to have, to my surprise, 720 elements, even though it has only 2 generators, but okay, fine. And then if I want to list all the 720 elements of H, I can type that in. I thought I might regret doing that, but it wasn't too bad. You could list all, you could see all the cycles are listed. Okay, then I'm going to create a new subgroup K. Let's create a smaller one. I decided. Let's create the one that's just generated by O. Okay, and then that's a much smaller group. It's this empty cycle is just the identity element. As a function, that's the function that sends 1 to 1, 2 to 2, 3 to 3, and so forth, the identity function. Okay, and then here are the other elements. These are going to be powers of O. Okay, and then the order of K is 6, and that's not surprising because the order of O is also 6. And it's a general fact that the order of an element equals the order of the cyclic group it generates. So the cyclic group that O generates is what K is. Okay, then a couple other, just for some random functions. You can ask if it is a group a billion. And so the symmetric group is definitely not a billion. So I ask, well, is G dot is a billion? And it's false. So these symmetric groups are our first encounter of non-abelian groups. For starting with S3, that's non-abelian. Matrix groups are another example of non-abelian groups. But okay, on the other hand, K, the subgroup K, is a billion. When I ask Sage that, it says yes, it's a billion, and that's no surprise because K is a cyclic group. It's a cyclic group generated by that element O, and so we've seen in it's the easy theorem that I proved in a lecture that every cyclic group is a billion. Okay, let me stop here.